Okay, so today is the deadline for what's called the early alert system, and what it is all faculty are required to go through their rosters, look at their students' grades up to this point, determine what their grade is, and if they are at risk, then we're supposed to put a check mark, and then we're supposed to select out of these options like why the student's at risk of not passing the class. And so anyone that had 65 or lower in this class got checked as at risk, and then the reason you're at risk is it says you're not meeting the requirements of the class. So I had to do this. An email was sent out to anybody who is at risk, and it says that you need to get in touch with me and all this stuff, and really I don't have any control over that. So I'm just letting you know, if you got an email saying you're at risk, I'm basing it solely off of the quizzes. We still haven't had an exam in here. So, you know, if you want to wait till the first exam to start feeling like you're at risk, that's fine. But just want to let you know, like I didn't go, you know, send out an email on purpose to each one. I had to do it as required, okay? The next order of business was the mistake I made in the formula on the notes from last time. So, you know, I understand we're all human, right? We all make mistakes. But that mistake that I made is worthy of lashings. Like when I get to face the math gods at some point, I will deserve the lashings I will receive for not having the correct formula. Number one, not having it, but then not recognizing it and doing an entire example off the wrong formula. It just goes to show you, I mean, my brain was totally somewhere else, and I shall be punished for that one day. And I will accept that punishment. I deserve it. So anyways, this is the corrected formula. I sent an email about this. I redid the video to correct it and everything else. So if you didn't see that, just be aware that I did go and address that issue. Okay. Now, you had a bonus opportunity for a proof of a reduction formula. So if you have that, I'll accept it now. I will not accept it later. So go ahead and bring it on up. Now remember, you know, at the end of the class, when you're asking, you know, is there anything you can do as far as to boost your grade up and stuff, I'm gonna go back and say, remember these bonuses I offered. You know, that's your opportunity to get points in the class. Thank you. Okay, last call. Questions on homework or anything else? Okay. All right. Let me crack my book open real quick here. Oh, and you know, it's been brought to my attention that in my solutions to some of the even problems that I have on Canvas, there's a few that have some rightos, some mistakes. Those were done like 4 or 5 years ago, and I've just never updated them. So if you find little errors where I'm off by a sign or something, you know, bring it to my attention. I'll say, yes, you caught that. Good job. But they're not any like major catastrophe things like this one, like that thing. Okay, number 9. What about it? Just, what about this one? This is eerily similar to the quiz problem. The quiz problem was just natural log x, wasn't it? So the idea was when we took the quiz over was it last time, where we had the natural log x on there? The idea was that you had done this problem already so that you were ready for this, ready for the quiz problem. So we don't want to fall behind. I've said this before. You do not want to fall behind this class where you're still doing homework from 6-1. I'm not calling anyone out. I'm just saying you don't want that to be the case in this class. It'll be very difficult to keep up that way. Okay, so I'm assuming you did a integration by parts here, and you chose your u to be the only thing it could be, right? And that forces your dv to be dx. Now you have to come out here and generate your du, and you have to generate the antiderivative of dx. So du here would be what? 2 over 2x plus 1. So that's already accounting for the chain rule there. And then your dx. And then the antiderivative of dx would just come up here to be x. You're okay up to that point? Okay. So now you set up the ultraviolet minus voodoo. So here's your ultraviolet. And then minus the integral voodoo, which will just be x times this fraction dx. So I'm going to put that x on top. So 2x over 2x plus 1 dx. Okay, now I'm going to follow you until you get to the point that you're asking questions. So what did you do at this point? Okay, so this is where the issue is. Okay. Okay, well, a substitution is going to work just on this integral right here, which I'll move down here. So I'm doing integral 2x over 2x plus 1 dx. And I'm going to make a new substitution now. When we say substitution, just a basic substitution. The basic substitution is I'm going to let the entire denominator be my u. And the derivative of that is what? 2 dx, yes? So you have a little bit of an issue here. If you take that integral and you rewrite the integrand, see if you agree with this or not. Just sliding this 2 over here to the dx. I'm doing that just to get it to match up, like our 2 dx matches exactly 2 dx. And so I'll be able to replace this yellow with what? du. By the way, if you work this a different way, there's like 3 or 4 different ways that you could have done this. Just FYI, this is not the only way. I'm just following kind of wherever I'm being led here. So, so that's going to be du. The 2x plus 1 is going to be replaced with u. But the issue is, what do you replace x with? So solve this equation right here for x. Okay, so if I solve that for x, I get u minus 1 equals 2x. I'll multiply both sides by a half. 1/2 u minus 1 equals x. So I'm going to replace x with this. So let's rewrite this entire integral. This integral will become the x on top, which is a 1/2 u minus 1. The bottom, which is just u, right? And then du here. We good with that? And now I'm just going to take the 1/2 out of the integral because it's a constant. I have u minus 1 over u. Any ideas there? Split it into 2 integrals. So we have 1/2 integral, or 2 fractions, sorry. 1 minus 1 over u du. So because we had 2 terms on the top, 1 on the bottom, split it into 2 pieces. And then these should integrate fairly easy. Antiderivative of 1 would be u. So this equals 1/2, let's see, u, and then I'll distribute the 1/2 minus 1/2. Antiderivative of 1 over u is ln u. I'll have a plus constant. I'm just going to tack it on to the final answer. What was u? 2x plus 1, right? And the u I'm talking about is this u, not the u from up here, even though they turned out to be similar. They're not the same u. So I'm going back to this one. So it'll be 1/2 times 2x plus 1 minus 1/2 natural log 2x plus 1. And that piece right there will get plugged in for this integral. So you'll be subtracting everything down here. That make sense? I believe that. Well, a lot of times when you look at the back of the book, their answer and your answer are correct, but it's just a, you know, it's, yeah. So I would challenge you to try and make them look the same. What's the back of the book look like? What is it? What's, no? Is that right? Like this? 1/2 2x plus 1 times natural log of 2x plus 1 minus x plus c. That's what it has? Is this minus x inside with this? Like in parentheses? Just like this? Just like this? Okay. So, where's ours? Right here. Okay, so I'm going to take this and I'm going to plug it in up here. So if I plug it in right up here, I'll have equals x natural log 2x plus 1. Then I'm subtracting 1/2, so I'll have minus 1/2 times 2x plus 1, and then I am subtracting a negative, so I'm adding this natural log, half of it, plus a constant. All right, if you distribute 1/2 through here, you get negative x, then you get minus 1/2, right? If we distribute that. And then, what else do we have? What if I put this and this? Can I put these together? No. Look at what this is right here. Look at this right here. You want to, let's factor out a natural log, 2x plus 1. Factor it from here and here. If I pull this out, I would have natural log 2x plus 1. What would be here if I pulled out the natural log? An x. What would be here if I pulled out the natural log? Plus 1/2? Yes? And then I have this still, right? Minus x minus 1/2 plus c. Are these the same? Distribute 1/2 through here. What do you get? X plus 1/2, that's this. Natural log 2x plus 1, that's this. Minus x, right? What about the minus 1/2 plus c? Just, it doesn't matter, right? You don't know what c is. Negative 1/2 plus c is a constant. So is c. You don't know what they are. So anytime you have a constant by itself like that, you can always just throw it into the c. So they are the same. I hope that made sense. Okay, I encourage you, if you have questions on homework, please come, by and get some help. Yes? What's that? Yes, it'll all be part of today's notes. Yeah. So, make sure you come by. I'm happy to go over problems. We just can't eat up too much class doing it, all right? I think 15 minutes is about as much as I ever want to do for any homework questions. All right, let's pick up. We're going to have a quiz today, but it's going to be at the end of class, and it's going to be a group quiz, all right? So you'll be able to work together on it. Careful what you wish for, though. Okay, no, I'm kidding. All right, so last time we ended class, and I had you go home and take a look at those two integrals, and said we would come back and pick up after that. So I am assuming that you know the antiderivative of secant x is natural log of secant x plus tangent x, and that there is also an antiderivative of secant cubed, which, is it on your formula sheets? I forget if it's on the formula sheets or not. It's not on there? Yeah, not to the third. Okay, but it is on page 321, okay? It's on page 321. Uh, not just yet. I just want you to know it's there. So it's 1/2 secant x tangent x, and then plus natural log secant x plus tangent x plus c. So if we run into an integral that has just secant, we don't need to do anything. If we have secant cubed, we don't need to do anything. We're going to just use that formula, all right? Now, we are going to get into a new type of integration today, right? Up to this point, we have basic formulas like antiderivative cosine is sine, power rule, x to the n, right? We have the formula for doing antiderivative x to the n. And those aren't really techniques. Those are just like, okay, you got to just know those, right? Then we have basic substitution. You're trying to look for u and its derivative somewhere in the integral. Sometimes it doesn't work out that way, but the substitution works. Then what's after basic substitution? Integration by parts. That's where you pick a u, you pick a dv, and you go backwards and make your little table. After that, we did trig integrals. Trig integrals were integrals that involve trig functions, right? Now we get to the next technique. It's the second to the last technique, and that's what's called trigonometric substitution, all right? Sometimes we'll just refer to it as trig sub. I'll just say trig sub, all right, as opposed to u sub, right, which is like what we were considering our basic substitution. So trig sub is very different in terms of you're not looking for something in its derivative anymore, okay, when you use trig sub. What you're looking for is that your integrand has a certain format to it. And the formats that we're going to be looking for, let me scroll down, are one of these three formats. If the integrand has a square root with a constant squared minus a variable squared. So if you have that anywhere in the integral, you might start thinking trig substitution. If you have square root of a constant squared plus your variable squared, you'll be thinking trig substitution. If you have square root of your variable squared minus your constant squared, anywhere in the integrand, you'll be thinking trig sub. You'll be thinking it. It may not be the best way to do it, but you'll be thinking this is what we like for trig sub. Now let me try and explain why and how trig sub works. And it's not very natural, all right? So here's the idea. Let's say that you have an integrand that has this square root in it. So you have some constant squared minus x squared. Then we're going to make a substitution. And this substitution is not, like I said, it's not a natural one. All we're going to do is we're going to replace the x in this problem, in this integrand. We're going to replace that x right there with a sine theta. Why would we do that? X was x. Why are we making x more complicated, right? We're going to call x a sine theta now. It seems like things would get worse. But here's what happens. If we do that, then a squared minus x squared becomes a squared minus, well, this is what x was, right? X was a sine theta. So if I square x, square both sides up here, I'm going to get a squared sine squared theta. So this right here is just this. Y'all follow? Okay. Now, from this, these both have an a squared in them now, so I factor out an a squared, right? Which leaves me with the 1 minus sine squared theta. But this is cosine squared theta by the Pythagorean identity. So this now becomes a squared times cosine squared theta. And if I take the square root of this, the square roots and the squareds go away, and I'm left with a cosine theta. So at the end of the day, this square root turns into a cosine theta. What's happened, though, is we've switched from the variable x to a new variable theta, haven't we? Which means when we're done, we're going to have to switch back to x when we get our answer. But it takes a complicated expression, which is a square root with a quadratic underneath it, and it turns it into a very nice cosine function, which is easy to integrate, theoretically. Yes? All right, now in addition to this, remember that when we did substitutions and integrals, we not only had to replace, like make our u substitution, we had to replace dx, didn't we? Like we had to go in there and replace that dx in the integral. Well, let's take a look at what dx would be for us. Remembering that x was a sine theta, take the derivative on both sides here. The derivative of x with respect to theta is dx d theta. The derivative of a sine theta, remember a is a constant, derivative of sine is cosine, so the right side just becomes a cosine theta. Then remember how we move that thing to the other side? Just going to move the d theta to the other side, and we get this. So not only can we replace that square root nasty thing with a cosine theta, we can replace the dx with what? A cosine theta d theta. Yes? And then we look at that integral. It all has cosines in it or trig stuff in it, and we try and do what we did last class with trig integrals. Okay, let's take a quick vote to see if you have any idea what the heck I'm talking about. Like if this makes any sense at all, yes or no? Okay, well, seems about right. I'm not going to explain it anymore, all right, because that's the idea. Once you see it in practice, maybe then you'll come along, all right? So we're going to do an example, but just remember, if you see this, right, a constant squared minus your variable squared, that will become a cosine theta. The dx will become a cosine theta d theta. As long as we're making this substitution, x is a sine theta. Now, after we do that, we rewrite the problem and hope it turns out to be a doable integral. I don't know if doable is a word, but I used it. So let's try this. So let's now look at this integral, and let's just remember that we have all these other techniques, right? So do you see like a basic substitution here? Do you see something in its derivative? Not really. I mean, kind of, but not really. The derivative of x cubed is what? 3x squared, and you have an x squared. What's wrong with it, though? It's trapped underneath the root, right? You're supposed to have it all by itself so you could slide it out next to the dx. Can't do it here. But what you should see is that what's in blue there, that's like a square root of an a squared minus x squared. Yes? Where a would be what for us here? 4. Okay, so let me start this out. I have integral x cubed square root 16. Can I just write it 4 squared? Minus x squared dx, like that. Okay, since I see that, I have the form that I like here. The form I have, square root a squared minus x squared, which means I'm going to make a substitution. X is going to be equal to a sine theta. So in green, it's hard to tell that's green. Can y'all tell that's green? Not really, huh? It still looks black. Okay, so that was supposed to be in green, so I'll just box it. This is my thought here. I see that form in the integrand. I know that means I'm going to use the x equals a sine theta substitution. So now let me formally actually do this. X for me here will be replaced with what? 4 sine theta. Now, what do I know dx is going to become? Now, you can either go off of what I had boxed in the notes, right? You can either just try and memorize this right here, that if x is a sine theta, dx will be a cosine theta, or you can just do what? Take the derivative. What's the derivative of 4 sine theta? 4 cosine theta, but don't forget this part. 4 cosine theta d theta. All right, and then the all-important step, what does the square root of the 4 squared minus x squared become? What does that become? So going back here, this should turn into 4 cosine theta. You do not have to show why this right here turns into this. You don't have to show it. That's part of what's nice about having this trig sub is you know if you make the substitution x is a sine theta, you know what dx is and you know what that square root's going to turn into. Now, if you wanted to show it, which you don't have to, you would just say so you're replacing the x with 4 sine theta, you square each one, you get this. Then you factor out a 4 squared, left with 1 minus sine squared theta. And then what does 1 minus sine squared theta become? Cosine squared theta. Then you take the square root, and then you'd get your 4 cosine theta. Again, I'm not going to show it. I'm not going to show it every time. I wouldn't ask you to show it every time. But I just want to make sure you understand where it comes from. It comes from this. Okay. If you do that, we should be able to rewrite the whole integral now. Any questions? Let's take a poll if you're good with me up to this step. Yes or no? Okay, let's keep rolling then. Here comes the integral. This integral will become a new integral. What about x cubed? It's this right here. This is x, right? 4 sine theta. I have to cube both sides, right, to figure out what x cubed is. So let me just do that right here. If I cube the left, I get x cubed. If I cube the right, 4 cubed is 64, and then sine cubed theta. So this x cubed will be replaced with 64 sine cubed theta. Okay, what about the square root of 4 squared minus x squared? That's going to be my 4 cosine theta. So I multiply that times 4 cosine theta. And then, what does my dx become? 4 cosine theta d theta, right? 4 cosine theta d theta. So I have dx is this. I have the big root thing here is this. And I have this is this part, right? That's everything being translated down into its different pieces. And now I proceed to put all this together. I have a big constant here, right? What's the constant? 64 times 4 times 4, which is, what is it? Did you get it? 64 times 4 times 4. 4 to the 5th. 1024. Okay. Then sine cube theta cosine what? Squared. Are y'all there? Right, you had 2 cosines there being multiplied. So now we're back in last class, right? This is a trigonometric integral. You have sine to an odd power. You have cosine to an even power. What do you do in this case? Factor out a single factor of sine and rewrite what's left in sine in terms of cosine. So I'm going to leave the 1024 out here. I'm going to rewrite this as sine squared theta, cosine squared theta. Here's the single factor of sine that I pulled out. And I'm going to remember from last class and all the homework I did and everything, that sine theta that I pulled out is going to be my derivative. Like, that's my du. And I'm going to be replacing cosine with u. But first I need to get rid of this sine squared and rewrite it as what? Rewrite it as 1 minus cosine squared theta then I have cosine squared theta, then I have sine theta, then d theta. And at this point, you should be able to make your substitution from last class. So what did we say u will be here? U will be cosine theta, and then du will be negative sine theta d theta. Do I have negative sine theta d theta? I have sine theta d theta. I don't have negative though, right? So got to get that negative on the other side. So how about negative du is equal to sine theta d theta? I mean, look at this problem. First, we had to do a trig substitution, right? Now we're doing a trig integral, but the trig integral requires a basic substitution at the end. So these are good test problems, right? I mean, it's all here. Everything's here. Except integration by parts. That's not here. I'm sure we could make one that has integration by parts in it too. No. Okay, can I rewrite this integral now? How about the sine theta d theta? Let's replace that with the negative du. So this piece right here is going to basically go away, be replaced with negative du. I'm going to pull that negative out in front right now. So this integral now becomes negative 1024. Okay, integral, what's this now? 1 minus u squared times u squared times du. I'm out of room. So I'm going to take this to the next page. And before I integrate, I'm going to distribute the u through, the u squared, sorry. To get this. Now, this is power rule, right? Just a power rule. So the antiderivative of u squared is 1/3 u cubed. Antiderivative of u to the 4th is 1/5 u to the 5th plus a constant of integration. My negative 1024 is just sitting out there. Does 3 go into 1024? No. Does 5? No. So I can't distribute this through and hope for anything cleaner. Now I need to go back and replace u. What was u? Cosine theta. So this is 1024 1/3. This is the same as saying cosine cubed theta minus 1/5 cosine to the 5th theta plus c. Okay, let's take a poll. We're not done, but let's take a poll and see if we're all together or not. Or let's see if at least 80% of us are together. Yes. No, it wouldn't matter. I mean, you could, but it would still be a constant. You still don't know what it is. So, are we done? What now? You got to get everything back in terms of x, right? In terms of x. Right now you're in terms of theta. So here's what we would like to know. I would like to know what cosine theta is, right? Cosine theta. Let me go back to the previous page. Let me figure out where I made the substitution. I made the substitution right here, didn't I? This right here? I said x was equal to 4 sine theta. That equation right there is very important in the problem because what it does is it is your connection between x and theta, right? It's your connection. So if you want to get cosine theta back in terms of x, you're going to have to somehow use that equation. So I'm going to take that equation, I'm going to write it down on the next page. Now, remember, x was equal to 4 sine theta. Would you agree that that's the same as saying this? X over 4 is equal to sine theta. Just dividing both sides by 4. Yeah? And now what I'm going to do is I'm going to draw what's called a reference triangle. I'm going to create a right triangle. And I'm going to label it, and I want you to tell me about this triangle. If I call the angle inside theta, and I call the opposite side x, and the hypotenuse 4, do you agree that this triangle is a geometric representation of this equation? Yes? So all I'm doing is I'm taking that equation, and I'm just writing it visually. Sine is opposite over hypotenuse. So that's correct, right? If I had x here on the hypotenuse and 4 here, that would not be correct. So there's only one way you can draw that triangle to match this equation. Now, what is it that I'm interested in? I want cosine theta. Well, cosine theta on this triangle is adjacent, sorry, I'm pointing here, I'm saying adjacent, is adjacent side over hypotenuse. You don't know the adjacent side unless you solve it using the Pythagorean identity, a squared plus b squared is c squared. So would you agree with this? If I label this side, I'm going to just call it a for adjacent. Do you agree a squared plus b squared is the x must equal c squared, which is 16? So this squared plus this squared is this squared. You can solve that for a. Okay, so a squared is equal to 16 minus x squared, which means a is equal to the square root of 16 minus x squared. Is that okay? So what is cosine theta then? Adjacent over hypotenuse. Adjacent over hypotenuse. So cosine theta should be square root of 16 minus x squared divided by 4. Let's see if you understood that, yes or no. It's called a reference triangle. Now, maybe somebody caught this, I don't know. How many of you caught that we already knew that what cosine theta was from earlier? We did, didn't we? Because when we made this substitution, do you see, where is it? Right here? See that right there? We already knew that this was square root of 16 minus x squared was equal to 4 cosine theta. We could have divided by 4, and we would have been there. Yes? But it only worked out for this particular problem. In other problems, that information may not be there. What will always be there is this one, because you will always have to start with the substitution. You'll always be able to create a reference triangle off that, and you'll always be able to recover all the other trig functions from that triangle. So I'm showing this to you as a guide to help you, that'll help you get through all sorts of different scenarios, as opposed to getting lucky like in this one. Hope that made sense. Yes? Where? I can't do that, because there's subtraction. You can't do square root of each one, right? For the same reason, when you square a binomial, you have to FOIL it, right? When you square x plus 2, you have to do FOIL. You can't do x squared plus 4. Square roots work the same way. Okay, I think I'm ready to write my answer. Okay, this is going to be negative 1024 times 1/3 cosine cubed. So that's going to be this root 16 minus x squared over 4 cubed minus 1/5, then root 16 minus x squared over 4 to the 5th power, and then all of that plus c. Sorry, my little plus c's there. I'm sorry? How do you figure? Is this too hard? Is this too hard? This is what Calculus 2 is. I'm not going to sugarcoat it. I mean, this is what it is. I mean, honestly, I have an honest conversation with you. You have to enjoy this stuff. You want to be an engineer? I mean, I know some people have to take Cal 2 just because it's part of their pharmacy requirements, something like that. You want to be an engineer, this stuff needs to actually light something in you. If this stuff is like, are you serious? Like, this sucks, man. I mean, if it's that, then maybe you should consider some other path. I mean, you have to be real with yourself. You want to do something you love. You have to find pleasure in the challenge and then the achievement of getting through it. If that doesn't light you up, then, you know, what do you expect in a job that would require you to face challenges and attack them? Yeah, I don't know. Maybe I should just shut up and just explain, just show. But I mean, I get concerned. Yes. Well, okay, I was never good at this in the beginning either, you know? I mean, that's the thing, but I enjoyed the challenge of it. And eventually I got good at it with time. Now, it does happen where you may have all the desire, all the passion, but you just don't ever get it. And then you have to be honest with yourself. I mean, like, when I was going up through school, I wanted to be a pilot. Okay? I get sick on roller coasters. I want to be a pilot all through high school. I want to be a pilot. I never was real with myself. Like, okay, look, I physically cannot do that. I mean, now it's different. I mean, we're talking about the mental thing here, but it's sort of the same thing. I mean, you have to face, you know, yourself in the mirror and say, look, if one, do I enjoy this? Two, is what I'm getting out, if I'm putting in 10 hours, am I actually making progress? If it's taking me 30 hours to do 3 problems, is this really what I want to do? Is this really the thing for me? I don't know. I'm trying to help you help yourself, you know, but I don't want this to be looked at as like I'm trying to make calculus too hard. This is the bar for Cal 2. This is it. This is the type of problem. It's the bar for everyone who's taking Cal 2 and everyone who will take Cal 2 afterwards. So, you know. All right, so we're not done. Still we're not done. Because when you cube a square root, you actually have 3 of them, so 2 of them can go together and get rid of a root. So that's going to clean up. I have to cube the 4, and then that's going to actually clean this up a little bit. And then I have to, what, 5th power on this 4, that will clean with this, and then this to the 5th power is going to get to become something even more. So, but that's where I can say ... We've gotten it to a point where I'm content. That is an answer on the test. Yes, it is. I don't believe I would take off anything if you didn't go any further than this. Now, if you're trying to match the book answer, be aware that that's the algebra that needs to be done. And I encourage you to do that because it's just practice on your algebra. Okay. Wow. So shall we just go through it real quick, or are we good? Move on? Move on? We'll move on. Okay, now that is what we do if we see the square root of a squared minus x squared. So you might be asking yourself, well, what if you didn't have that? What if it was a plus? Well, there's 3 different scenarios we can have. We can have a constant minus our variable squared. We can have the constant plus the variable squared. Or we could have the variable squared minus the constant squared, or the constant. Constant squared, constant, same thing, right? So in any of, those are the only 3 variations you can have in an integrand. There's no 4th option. So we have 3 different approaches. If it's this approach, like the one I just showed you, this is the substitution we make. If you have addition between the 2, we do a different trig substitution. Instead of doing x is a sine theta, we do x is a tangent theta. Now, if we did that, you have to believe that this would become this. Now, why is that true? Let's see if we can do it mentally. What would this x squared be? A squared, tangent squared. What could you factor out of both? A squared. What would be left? 1 plus tangent squared. What's 1 plus tangent squared? Secant squared. So you'd be taking the square root of a squared secant squared, which would leave you with a secant theta. Same approach as the previous one. Your dx, where does this come from? Derivative of a tangent theta. Well, what's the derivative of tangent theta? Secant squared theta, d theta. The a is a constant, comes in front. So those three will always come out if you have this format. If you have this format, then it's a different substitution. It's x is a secant theta. Let me ask you, if you do this versus this one, the only difference is the signs, right? This is positive x squared, negative a squared. This is positive a squared, negative x squared. Why can't you make these look the same by just factoring a negative 1? Like if I pull a negative 1 out here, then this would become, wouldn't it be x squared minus a squared? Wouldn't that be the same thing right in here? Distribute that through. And these two are the same except for the negative. So can you take the negative out of the root? No. That's why they are different. They're distinct. You can't pull a negative out of a root. So that's why we have those two scenarios separated. Unless you have I, and we're not allowed to do that here. Okay. I guess I can leave that there. So here's some examples, 3 examples, and then we're going to be done with this section. So let's see how these turn out. All right, so I'm thinking right now, do I see a basic substitution? Not really. Do I see integration by parts? So that's where you choose one to be u, the other one dv, and you make your table? I don't know about that. I don't think so, because if I chose, I don't know, what would you choose for v? I mean, for u? You could go x to the negative 2, but then derivative of that would be negative 2x to the negative 3, and antiderivative, okay. After a little bit of thinking, I realized that's probably not the best approach. In fact, now that I've been thinking about trig sub, I see a square root, and I see underneath it variable squared plus constant squared, right? So the form I have in this integral, the form that I have is a square root of x squared plus a squared. Now, let me go to the notes. It's the second type, isn't it? It doesn't matter if I write a squared plus x squared or x squared plus a squared. Doesn't matter, right? The same thing? So I'm in that second one. So what I should do is make a substitution that x is a tan theta. That should be my substitution. X is a tan theta. So I'm going to make a substitution. X is equal to a tan theta. So now, let's go ahead and do this. For me, x will be equal to what? 3 tan theta. So far, we haven't had any issues identifying what a is. because, you know, the previous one, it was, what, 16 was there, so it was just 4 squared. This one's 9, so that's 3 squared. We'll do one. In fact, we'll do one in a little while where it'll be a little bit harder to identify. Okay, so that's the substitution. I can get dx without having to refer to the table, like the notes, because I can take that derivative. It's just 3 secant squared theta d theta. The only thing I may not remember is what this turns into. What does this root turn into? Without me actually mechanically doing it, I just go to my notes. That's going to turn into what? A secant theta. A secant theta. So for me, that's what? 3 secant theta. Okay, quick vote to see if we're all okay on the same page. Next thing to do is what? Rewrite the integral. Just rewrite everything. I have a 1 on top. Yay. Okay. X squared, bottom left corner. What's x squared by itself? Well, that's this x is this, right? So just square both sides. You get 9 tan squared theta. Right? Squaring both sides there. So the bottom left corner is 9 tan squared theta. What's that whole square root down here become? 3 secant theta. Oh, no square root. 3 secant theta. So the root thing is here. The x squared here is this piece. And what am I forgetting here? dx. Do not forget dx. What happens if you forget dx? It's done, right? You're cooked. So dx for me is 3 secant squared theta d theta. No. If something was left over. Normally, with this, you should be able to get everything. What we will have to deal with is something that may happen with our theta, but you'll see that when we get to it. Okay. Any questions? Okay, we can we can start to clean this up. I do see that one of these secants will go away. I have a secant squared on top, which will kill off one of these secants. How about the 3's? The 3's will cancel. And then I can bring a 1/9 out of the integral. What do I have on top? Secant theta. What do I have on the bottom? Tangent squared theta. Then d theta. Now, if you look in the notes from previous class, we did have a way of attacking secants and tangents, but it was secant and tangent next to each other in the numerator. We didn't have them in a fraction. So what I recommend you do in this is to clean it up, rewrite it in terms of sine and cosine first. Let's just rewrite the whole integral, replacing everything in terms of sine and cosine. I'll go a little slow. Secant is 1 over cosine. So that's what's on top, over tangent squared, which is sine squared theta over cosine squared theta d theta. So all I'm doing is rewriting secant as 1 over cosine, rewriting tangent squared as sine squared over cosine squared. And now I'm just going to flip, and when I flip this, it becomes what? 1/9 integral, what's... Only one of the cosines will cancel, right? So you'll have cosine over sine squared. d theta. I'll just write it over here. Quick vote. Yes. No. Because it's multiplication, you can only cancel in one, not all factors. Each factor that cancels, they cancel one together. They don't distribute to more. I don't know if that makes sense. It's just, look, if you write 4 times 4 times 3 times 4, you can cancel 1 4. You can't cancel like that. Yes.
Like on quizzes and exams, when you go to Trig Sub, you want us to denote where theta is going to be.
Denote what?
The range of domain, like we're using, like if we're using like x equals 6 tangent theta, which is that theta belongs to negative pi over 2 to pi over 2.
No. No. We are just going to assume that this is the antiderivative for whichever values of x satisfy yes. Yeah. Could you? Yes. Now, no. No. Don't worry about domains. Not interested. Okay. All right. I've given you enough time to look at that. What do you do? Basic U sub. A basic U sub. Because you see something in its derivative. U is sine theta. What's its derivative? Cosine theta d theta. You have cosine d theta, cosine theta d theta. You have that up top, don't you? So that in yellow is your du. And your sine squared theta is going to replace with what? U squared? So this is going to turn out to be real nice. It's going to be 1/9 integral 1 over u squared du, which is really 1/9 integral u to the negative 2 du. What is the antiderivative of u to the negative 2? So it'll be negative 1, which I'm going to bring it out as a negative 1/9. U to the what? Negative 1 plus c. So there's your power rule on u to the negative 2. That's really 1 over u, isn't it? So this is really negative 1/9 times 1 over u, but what was u? Sine theta plus c. And what's 1 over sine theta? Cosecant theta. So here's where I am. I've got negative 1/9 cosecant theta plus c. Yes, because that would have gotten you there quicker, right? But you would have had to have recognized that. Some people will, some people won't. So, in fact, if you get an antiderivative that looks that simple, you should be thinking, well, wait a minute, this should have been just the derivative of this. What's the derivative of cosecant theta? Negative cosecant theta cotangent theta, which is what's up here. Yes. Yes. That's right. It's just one of those things with the bad notation we have in math with arc sine, and if you want to raise sine to the -1, it's different than sine to the -1. So you have to know in the context of the problem which one you're doing. Here we have, this has nothing to do with an inverse. This does not mean inverse. This means 1 over that, whatever that is. So if that is the sine, that doesn't turn it into an inverse function. It's just notation. I don't know if that makes sense. It's just notation. Yeah? No. There's no way to know difference in the notation. Are we done? Nope. Because your answer is in terms of theta, not in terms of x. So now I'm going to go back to my substitution. What was my substitution? X equals 3 tan theta. And do you see how this time, if you go back to our original substitutions, we know something about tangent theta, we know something about secant theta, right? Tangent and secant, we know. But what we're interested in is what? Cosecant. So there's nothing we have from previously that's going to help us get cosecant right away. We're going to be forced to draw a reference triangle. I forgot to divide both sides by 3. So take that, divide by 3. Now, reference triangle. Must be a right triangle. Theta is always going to be this angle. Tangent is adjacent over opposite, right? So this should be x over 3, or x and then 3. And that means to find cosecant, cosecant is the reciprocal of sine. So I need the hypotenuse, don't I? And I'm going to just solve that one. I'm going to put it in red because I'm going to not show the work for this. It's x squared plus 3 squared, so it's the square root of x squared plus 9. So let's go now and write our answer here. We've got -1/9 cosecant, which is hypotenuse over adjacent. Hypotenuse over, did I say adjacent? Sorry. Hypotenuse over opposite. Right. Cosecant is the reciprocal of sine. Sine's opposite over hypotenuse. Cosecant would be hypotenuse over opposite. And that requires no cleaning up. That's it right there. Questions? Let's take a poll. See if you follow this. I want to show you one more. I'm going to skip because I want you to have a little time for your quiz. Here's the last variation, okay? This one right here. I'm not going to do one like this, okay? But I want you to be aware, if you ever saw this, I'm not going to do one like that today. I may do one next class, all right? But today I'm not. But here's what I'd like to do. So I'm skipping B on the notes. I'm skipping B. Come back to it. I'm going to do C, or at least start C. I don't know if I'll do the whole thing. So how about integral? We've got, what the heck is that? X cubed over 4x squared plus 9 to the 3/2 dx. So what's sort of unique about this problem is that it doesn't automatically tell you by looking at it that it's trig sub, because you're missing the square root. I mean, it's not right there written for you, right? So maybe you think of like basic substitution and you start to try and figure out if integration by parts works, and you get stuck, and eventually you think, well, the only thing that maybe makes sense is a trig substitution. I mean, what I am happy about with trig substitution is the fact that I've got like something squared plus something squared. Constant squared, variable squared, kind of, with that 4 in there. I haven't had that yet, right? So let me rewrite this integral and force the square root to be seen. Now that's the same thing, right? Raising it to the 3 halves is the same thing as the square root cubed. Now I see a square root, but do I have the form that I need? Do I have variable squared plus constant squared? No, I have a constant in front of my variable squared plus a constant squared. I have to have it exactly a variable squared plus a constant squared. So what can I do? What's that? I'd have to pull a 4 out of both, wouldn't I? Okay, let's do that. I don't mind doing that. I just saw a different way of doing this. Okay, I'm going to pull a 4 out underneath the root. If I do that, I'm left with x squared, and then what? Plus, I have to pull it out of both. 9/4. You all agree with that? Now, can I take the 4 out of the root? Square root of 4 would be 2. Now, what if that was a 5? Let's just say. I could pull this out as a what? A root 5. I just couldn't do anything with that. So root 5 would just be a constant that would come out. But in this case, I'm lucky. I get to pull out a 2 out of this root. And then that's going to get cubed, isn't it? The 2 that comes out here is going to get cubed. So it'll be an 8. And that 8 can come out of the entire integral as a 1/8. Can I do all that? Okay. So square root of 4 is 2. 2 comes out. 2 gets cubed. That's an 8. Comes out as 1/8. There we go. That wasn't so bad. Now I still have x cubed down here over square root x squared plus 9/4, all of that cubed dx. All right. At this point, do I have variable squared plus constant squared? Yes. So this does have the form that I like. Well, I don't know if you like it. Square root x squared plus a squared. So the substitution we make is x is equal to a what? Tan theta. That's the form we'll use. So we didn't have a problem in the last few problems identifying what a was. But here, can you tell me what a is? 3 halves, right? It's whatever this is, take the square root, 3 halves, that's our a, isn't it? So just so we're all clear on this, what if this had been x squared plus 3? Then what would a be? Square root of 3. And it would just be an irrational number that you don't know what it is, but it would just be, it would carry with you the whole time, square root of 3 throughout your work. Fortunately for us, it's this one, in this case, just, 3 halves. So let's make our substitution. X will be equal to 3 halves, right? A tan theta. The derivative of this is 3/2 secant squared theta d theta, and I'm guaranteed that the square root of x squared plus 9/4 will turn out to be what? A secant theta. So 3/2 secant theta. All of this information is coming just off of this box right here, right? That's what that's coming from. All right, go ahead. That's why I was saying I saw a different sort of approach to this problem, but I didn't do that here. So let's just see what happens, okay? You couldn't cancel these. What you could do is you could rewrite it as this over this, all of that cubed. That you could do. But I'm going to leave it just like this. What will the x cubed be replaced with on top? Well, it's this cubed on both sides, right? So here comes my new integral. I have 1/8 out top or out front. What's 3/2 cubed? 27/8 tangent cubed theta over the square root of all this junk turned into what? 3/2 secant theta, but then I'm doing what to that? Cubing it. So when I cube 3/2, 27/8 again, over secant cubed theta. Am I done? dx gets replaced with 3/2 secant squared theta. 3/2 d theta. All right. Yeah, I'm going to get rid of those. Take a 3/2 out. I also have the secant squared kills off 2 of those, so I'm just going to have 1 secant on the bottom left, right? What constant's out front now? 3/16 integral tangent cubed over secant. I'm going to want this all in terms of sine and cosine, but I'll go ahead and write this down. Okay. So rewriting this, 3/16 integral, it'll be sine cubed theta over cosine cubed theta. The secant on the bottom reciprocates, right? It's 1 over cosine. It flips up, so I have a cosine on top. Cosine theta over 1 d theta. One of the cosines cancels. I'm sorry? Secant is 1 over cosine, but I flipped it up. I reciprocated it. Integral, let's see, sine cubed theta over cosine theta d theta. Oh, what? Was it cubed? Yeah, it was squared. Okay. Now what? You ready? What's that? Sine tangent squared, yes. But we don't have a technique for that. How about this? See if you follow this. Okay, what did I do? No, sine cubed is really sine squared times sine, right? So I peeled off a sine. I was left with the sine squared. I rewrote that sine squared as what? 1 minus cosine squared. Why did I do this? What is this going to turn into? Just make a u substitution here, right? U is what? Now, did I use u already? No, right? Let's let u be what? Cosine theta. Du is negative sine theta d theta. So when I make this substitution, I'm going to have a negative that's going to pop out. So I'm going to make that negative 3/16 integral 1 minus u squared over u squared, what? Du. Can you do that? Split it into two separate integrals? U to the negative 2 minus 1 du. Because that becomes 1 over u squared minus u squared over u squared, right? This over this is this. This over this is 1, but it's subtracted. Can you find the antiderivative there? Yes. So, is that okay? You think you can get it from there? I'm going to let you get it from there, because we have 20 minutes. You have to plug cosine in, then you have to do a reference triangle and go back and... But I think I've got it down to a point we like. All right, so here's what I was thinking we could do. I was taking a look at an old exam. And I have some integrals on here I thought we could do, but now that we only have 20 minutes, why don't I try and give you... Just don't... Sorry? Is it not on here? I think you can do everything now. Yeah, you can do all these. Well, you still may run into issues because I have not covered all scenarios. I mean, I didn't look at all of them, but... Oh, this page is wrong? Okay, that page is wrong. It's the section 462 homework. Man. All right, let's just do one problem. Let's just see if what you can do in 20 minutes with this one problem. This was taken directly off of an old exam. Everyone's going to turn in their own work, but you can work together. Yes. Well, it might. I don't care what you use. I just want you to practice, that's all. I just want to see that you can do this now that you've seen me do a couple. There it is. Okay, so for next time, make sure you do as much of your homework. 6.1 should be done by now. 6.2, do as much as you can. We will come back and continue 6.2 and then move into 6.3. Our first test, is it next week? No. Not next Monday. The one after that. which is good. Yeah, no. We have 2 weeks from today is our first test, and we're good on time. Like, we have a lot of time to keep practicing before this test. I'm gonna stop recording. I'm turning the lights on.